let's consider a system with a unidirectional depolarizer as a critical device. We see a depolarizer defined. The MT variable is actually defined as being 0.9. That means that we have a lossy but otherwise perfect depolarizer. And we're going to apply it as a down depolarizer, or a depolarizer that only operates in a single direction, as we did in the previous segment. This is a more complex application. Let's take a look at the graphic. This is a slab, such as a backlight, with scattering dots, a scattering, highly reflective diffuser on the bottom, and a couple of other layers which I'll describe in the 3D view. So you see scattering dots, you see rays bouncing around, a few rays bounce out the bottom, but what we really want to do is examine what's happening above the system. When we couple out of the backlight, we have a hybrid polarizer, and that hybrid polarizer lets one polarization be transmitted and reflects the complementary polarization back into the system for recycling, which results in a more efficient backlight design. We have above that a detector, and then we're detecting the irradiance coming out of the system. So let's zoom out to just appreciate that irradiance pattern a little bit. And now we'll zoom back in to talk about what the Mueller is doing for us. Before we get to this polarization splitter, we have light that has been diffusing through the system via scattering surfaces. So as we exit the system, we discriminate or strip off one polarization and let it transmit, while we reflect the complementary polarization back into the system. So this Mueller down depolarizer, as it's called, has no effect on light that is coming up. But light that is coming down off of the polarizer is reconverted to unpolarized, so it can interact with these diffusing surfaces without having to worry about polarization tracking. We're assuming that these diffusing surfaces would depolarize the light anyway, and this just gives us a convenient way to lump all of the depolarization in one place, which makes the whole task of modeling this system a little bit simpler. Now let's take a look at the same system, but in terms of its polarization purity coming out of the top. So I'm running exactly the same system, but I have added an analyzer, which is a crossed polarizer to the transmission polarization mode of that polarization splitting device here. And then I'm looking at a detector at the top to examine the polarization extinction of a crossed polarizer with that transmitted polarization. So now we see the extinction pattern for the analyzer transmission after going through that polarization splitter. So this gives us an idea of how good the polarization coming out of that polarization splitter really was. We see the Maltese cross pattern that we expect in high polarization extinction systems that operate at very large full angles of view. So here we're seeing a full hemisphere. This is straight ahead in the center, and to the extreme right is 90 degrees out of field, all the way out at the edge of the hemisphere, and correspondingly all the way out at the other edge of the hemisphere, the opposite edge. So this is a horizontal angular space, and then this is a vertical angular space. And we get good degree of polarization and therefore good extinction or low leakage along that horizontal line and along the vertical line. And if we were building a full liquid crystal device, our task would be to design a liquid crystal device which deals with the leakage in these four corners in a way that uses the light most effectively.